done before. So finally, multiple regression. So multiple regression, it's similar to simple linear regression. If you go back to the beginning of lecture 32, where we introduced all the matrix notation, I set that all up for you so we wouldn't have to redo this now. So we had k predictors. We showed that y hat equals x b hat defines a regression plane where b hat is, so it's defined as the argmin overall beta in k plus 1 variables, minimizing the Euclidean norm of the residuals y minus x beta. So beta hat minimizes this, and we used a geometric argument to show that beta hat was x transpose x inverse x transpose y. Let me just jump ahead to this picture here that shows essentially the regression plane, the mean. It even shows the residual distance, the model distance, and the total distance. So some facts from before that we talked about: theorem AB on page 573 to 574. The expectation of B hat's beta. The variance of beta hat is sigma squared x transpose x inverse, which is a k plus 1 by k plus 1 matrix now. In lecture 34, we showed that s squared was RSS over n minus 2 is an unbiased estimator of sigma squared. Now that we have, actually, if you looked at we proved that there, and you can see how that's going to generalize if we have more than one predictor, but it's proven on theorem A, page 576. S squared is RSS over n minus k minus 1. It's an unbiased estimator of sigma squared. And just like before, we have our decomposition of the total sum of squares as MSS plus RSS. The degrees of freedom now are n minus 1, k, and n minus k minus 1 respectively. And like we had above, our R squared is MSS over TSS, or coefficient of determination. We can define an F statistic as MSS over K, RSS over n minus k minus 1, which you can rewrite then in terms of R as R squared over K, 1 minus R squared over n minus k minus 1. So this is our test statistic now. So if we assume that our K predictors are independent, we can do an F test whether beta 1, beta 2, beta k are all 0. And for simple linear regression, we have only beta 1, and the F test is equivalent to the T test as mentioned above. So we didn't need the F test for simple linear regression, but we clearly need it now. If we reject the null, it's natural to ask which of the beta I are statistically different from 0, right? So that's exactly like what we did in ANOVA with the Bonferroni and so on. In other words, which of these variables x1, x2 up to xk have a relationship with y, in other words, are not independent. So as mentioned above, the variance of beta hat is s squared x transpose x inverse, and so we want to get our hands on beta I hat. We want to in particular get the standard error, or this standard error squared in this case. So that turns out to be right. So that's just the diagonal element, the II diagonal element in the variance covariance matrix above. And so it's a fact from Glantz's Applied Regression in ANOVA book that you can also write this as S squared over n variance xi 1 minus ri squared, which sheds some light on this standard error squared. Here, by the way, ri squared is the r squared obtained by regressing xi on x1, x2 up to xi minus 1, skipping xi, and then xi plus 1 up to xk. So, if k is 1, then r squared is 0, right? Because there's no other predictor, and you get s squared is beta 1 hat is s squared over n variance x, which is exactly what we got before. If k is 2, then r1 squared is just r12 squared, where r12 is just the correlation coefficient between x1 and x2. I just call it r sub 12, just so it's clear that it's the regression correlation coefficient between x1 and x2. So it follows that if xi is correlated with the other predictors, then the standard error squared of beta I hat will be large, since ri squared, the coefficient of determination, is close to 1, and the t-test for the null beta I is 0 will be useless. So that's why we need to avoid this situation where we have what's called multicollinearity, where the predictors are related to one another. So next, it's important to understand that r squared can only increase by adding more predictors. So this is because r squared is an in-sample measure of prediction accuracy. In other words, the predictions are checked on the subjects already present in the sample, as opposed to checking them on new subjects. So in particular, these are the same subjects on whom the model is fitted or trained. So r squared can be made to look very, very good by fitting models with lots of parameters. So I just want to make this a little bit more quantitative for you. So remember, r squared is 1 minus RSS over TSS, and TSS is the variance of y, and this is fixed when you take your sample. So we're going to argue that going from one predictor to two predictors decreases the RSS and hence increases r squared. So, so decreases, so it makes it closer to 1. So RSS is something that we choose our beta hat so that it minimizes the Euclidean norm, right, of the residuals. So RSS is the min arg of beta 0 in R. You choose the beta 0 and the beta 1 that makes the RSS as small as possible. And so the more predictors that you have, the better fit you can possibly get, because you're trying to minimize, you have more parameters that you can tweak to minimize the RSS, if that makes sense. So adding another parameter, there's no way that you can get a larger RSS. You have to get a smaller RSS, and hence r squared will get closer to 1, and hence f will also increase, indicating right. So just one last note here is we're not going to emphasize this at all, but you'll probably run across the coefficient of determination with the subscript ADJ. So so this is a deflation of r squared. So this is r squared adjusted, where we basically adjust for adding these additional predictors. And so I just make an argument that it does decrease r squared by taking the number of predictors you have into account. So it's been a long day. I hope you're all well, and I will see you on Monday. I hope. Have a good day.